So now we'll talk about applications of Bernoulli's equation, and a first nice illustration of how this is relevant is we can look at stream tubes and derive Bernoulli's equation from the concept of a stream tube. So what is a stream tube? Stream tubes are a collection of streamlines that form a closed loop. So if I have a closed loop here of all these streamlines, then I realize that there's no flow out of this tube, since by definition all the flow is along the streamlines. And that also means, from mass conservation, that the cross-section will tell us how fast the flow is, because mass conservation tells us that whatever flows in here per unit time has to flow out here. So let's look at a very simple 2D case first, before we consider the more general 3D case. From just the continuity equation, if we have in the 2D case two streamlines that have a cross-section as follows, and then we have some velocity u1, let's say there's a constant velocity here, so you have u1, a1, and a given density coming in on one side, and this only works for incompressible flow, so rho is going to be constant here. Then the distance that this water travels is u1 delta t. Now that is at the inlet. At the outlet, the water is going to have to flow a lot faster since the cross-section is smaller. So now here we will have a distance u2 delta t, where the cross-section is a2, the velocity is u2, and the density is the same rho. And then we know from mass conservation that simply the mass in has to be the mass out. So mass in minus mass out is 0. So what is the flux in over a time delta t? Well, it's the density times the area times the distance u1 delta t. And that has to be equal to rho a2. So rho and delta t cancels, and we have a1 u1 is a2 u2, very straightforwardly. And that means that if we know the cross-sections and the velocity coming in, then we can infer at what velocity the water is going to come out. And what that means is that if a2 is much smaller than a1, then proportionally the velocity at the outlet is going to be higher than that at the inlet. Now we will consider a general 3D case of a steady inviscid constant density flow, and we will look at a stream tube control volume to show that along a streamline the Bernoulli equation holds, i.e. along a streamline the stagnation pressure is constant, i.e. rho u squared. Yeah, so this scalar sum of three types of pressure is constant. And this is what we will show now. So I've inserted a schematic of a stream tube element here. So we'll use a small stream tube control volume of length ds. Now we'll say that this is at an angle theta to the horizontal, so dz is ds sine theta, which is relevant because gravity is going to point down. There'll be an extra pressure force at the distance ds relative to the original cross-section here. The original cross-section here has values pressure P, area A, density rho, and velocity u. The density is constant, since we said we have a constant density flow. And so that means at the further distance along up here, at the other end of our control volume, our pressure may have changed. So now we have P plus dP ds by simple Taylor expansion. And we only need to consider the first correction term since we're looking at a small control volume. So then A plus dA ds. ds is our change in the area, and the other thing that's going to change as a result is our velocity u. And this is capital U, du, ds, ds. So this is the geometric setup that we'll consider. Now, by definition, there's going to be no flux through the sides of the control volume. Everything is coming in through here and going out through here. Since this is all small, so these are approximately conical shaped control volume, and flux is perpendicular to the surfaces, which we will write as NdA, and no flux perpendicular to the sides. So the flux down here, U dot NdA, is simply minus U dA on the inlet. This is the inlet here, this is the outlet. Put this down here, inlet flux, it's minus U dA, outlet flux is plus U plus du ds ds dA. So if we integrate over the two surfaces, then we'll find from the conservation of mass, integrate over inlet and outlet surfaces, we will find that minus rho u a, simply a on that side, plus rho u plus du ds ds times a, and now this is the larger volume, which is just a plus dA ds ds has to be 0. So this is from conservation of mass. Next, we'll consider conservation of momentum, where the integral form is just given as. Comparing this to our diagram of the stream tube, we realize that this now at the inlet just becomes minus rho u squared a, and at the outlet it's the same as earlier, but just rho u plus du ds ds squared. Right, we have an extra u term here, otherwise the integral doesn't change, and the area of the outlet is as before. So this is the left-hand side. And then on the right-hand side, we have two terms, the gravity term here. So the gravity term you can show is going to be minus rho g sine theta. And then you'll take the average value of the body force. So the average value will be a plus dA ds ds over 2. That puts you at the midpoint, and then you time the area by the distance to get the volume. Yeah, so this here is your volume integral. The third term is the surface pressure on the surface of the control volume element. And what's important, you have to consider three terms here, the two sides and also an extra pressure force on the conical surface of the tube. So on the inlet, you just simply have the pressure at the inlet times the area. And at the out, so this is the inlet. At the outlet, you have
the outlet pressure, d plus dp ds,
times the area at the outlet, which is dA ds times ds,
plus the extra term, which is the extra pressure on the conical surface, which to a first approximation can be written as the average pressure over the tube, times the difference in areal size, which is dA ds ds.
So what you'll see here is that for the pressure almost all terms cancel apart from this product of dP ds ds times A. The PA here cancels with that. This second multiplication cancels with that. This is small, and this cancels with the one up here. So we are left with just minus A dP ds times ds. Now let me repeat the mass conservation equation here. So this is from the previous page. And let me label this equation A. And let me rewrite the momentum equation. And there you will realize that I can write this as u plus du ds ds times rho ua, and all the other terms are small here. So then I can write the momentum equation as and now I can take equation A and plug it into B, and you will find rho ua du ds ds is equal to minus rho g a plus dA ds ds dz, where for dz we've used sine theta ds when we compare it to up here, minus a dP ds ds from over here. Now let's divide by rho A. So I've skipped a couple of steps here, right? There's some simplification that you should make sure you can follow. And so then we have u du ds ds equals minus g dz minus 1 over rho dP ds ds. And you can already see now it is starting to look like the Bernoulli equation. So you can rewrite this essentially as the infinitesimal of a half u squared bu squared plus g dz plus 1 over rho dP. And then this will be equal to 0 along a streamline. And so now integrate that whole thing, and what you end up with really is just Bernoulli equation, u squared over 2 plus gz plus p over rho equals constant along a streamline.